Hello, hello everyone. This is Srinjay Ganguly, and I'm going to take the Shor's algorithm now. So I am unable to take today's evening class because I have to urgently go somewhere out. So therefore, I am providing this pre-recorded lecture so that you can refer to this. And in the morning today, we covered the theory and the derivation, the proper detailed mathematical derivation of Shor's algorithm. And those of you who attended the lecture, I really appreciate you. And we solved an example for a is equal to 13 and m is equal to 15, where 15 number m or n, you can take any variable, needs to be factored into prime factor. That means the factors which we will be considering should be prime numbers, right? It should be prime numbers. That is the goal of Shor's algorithm. So we have discussed this today morning, and now I am going to show you the Qiskit example of this. Okay, so this is the Qiskit implementation of the Shor's algorithm. Now this is the same modular exponentiation circuit which we have seen in the theory lecture. This is the one. So this is the circuit, and now what we are going to do is that we are going to solve a simple example. So we are going to use the formula ay mod n to solve a simple example where we have where a is chosen randomly, as you know, in the Shor's algorithm, which you have already seen in today's morning lecture. A is chosen randomly and n is the number which needs to be factored. So that is what we do, and based on this, what we are going to do, we are going to construct the unitary operator for the given a and the n value, and therefore for any given a and any n value, this method will be able to work. So we are going to use the formula ay mod n, where a is equal to 3 and n is equal to 14. Okay, so we are going to use this formula to calculate. So u applied, that means the unitary applied to the y, where y is your ket psi. Okay, and now we apply that. So as you can see, this is very simple formula application, and we keep doing this calculation. Okay, as you can see, y will start from 0 1 2 3 4, and it keeps on going, and we keep on doing this calculation until it starts repeating. That means again 0 3 6 start appearing, right? So if you see, if you keep on doing this calculation, you will see that in the 14th one, in the 14th state, it again starts repeating. As you can see, we have again arrived at 0, and then in 15 we again arrived at 3. So therefore we are able to find the we will be finding the period using the Shor's algorithm based on this. And now what we are going to do, as you can see, we have total 15, that means total 16 quantum states, and now we are going to construct our unitary matrix. So let us say we start with here. So this is 0 0 0 0 0 0 0 0, then this is 0 0 0 1, and so on up to 15. And based on these numbers which we have here, what we are receiving, like here, if you can see my arrow here, whatever value we are receiving for that particular zero. So let's say these are all the column values. So let's say you mark all these columns: ket 0, ket 1, ket 2 up to ket 15. This last one is ket 15. Okay, and then according to that, you are going to put the value 1. Okay, because that value is activated, therefore. So for example, for the 0, in the column 0, you have 0 0 0 0, and 0 0 0 0 corresponds to this row, right? So we are going to put the row value. Similarly, if you can see, for the 1, for the 1th column, ket 1th column, we have 0 0 1 1, which corresponds to this row, right? Which corresponds to this row. So you can write all those stuff. So this will be starting from ket 0, the column ket 0, ket 1, ket 2, ket 3, ket 4, ket 5, and so on up to ket 15. And on the row wise, you can write 0 0 0 0, like the binary notation, and 0 0 0 1, and so on. So in the column, you write the decimal notation. In the row, you write the binary notation for your convenience, and then you can mark these states accordingly. For example, if you see the column 2, this is the ket 2 column. Okay, it says that the value comes out to be 0 1 1 0, which comes here. As you can see, this is 0 1 1 0, right? This is 0 0 1 1, right? This one is 0 0 1 1, and this is 0 0 0 0, right? So I hope that you understand that when it starts repeating, as you can see, it starts repeating from ket 14 value, right? Ket 14, ket 15. Therefore, you just put 1 on them. Okay, you are not going to put again, you are not going to mark again 0 0 0, because that is already marked, right? So therefore, you are going to put 1 on them. So as you can see, I have put 1 on the 14th, ket 14. This is the ket 14 column. And here also it is 1, it is not visible, but it is also 1. This is also ket 1 on the 15, ket 15. Okay, so you put 1 onto those where it starts repeating, right? And in this way you are going to form this unitary matrix, and therefore this unitary matrix is customized for a is equal to 3 and n is equal to 14. Okay, and now with the help of this unitary matrix we are going to draw it in Python. So as you can see, here we have 1, here we have 1. So this is ket 14, ket 15 column. Okay, this one, as you can see, look at my cursor here. This is ket 14, this is ket 15. Okay, and you are going to mark them as 1 1 because here they start repeating. Okay, here they start repeating. And now what you are going to do, you have formed this unitary operators, therefore we define our QFT dagger, which means the inverse QFT operation. This we have already seen morning in today's the Qiskit implementation of quantum phase estimation, and I have mentioned this multiple times in the past also to everyone, that we are going to use quantum phase estimation as a subroutine or a sub part of algorithm, and quantum phase estimation cannot be used individually. Using it individually does not make any sense, therefore it becomes a subroutine of a algorithm, and here we can see that it is indeed a subroutine of the Shor's algorithm. Okay, and this is the same code. Okay, this is the same code which you have seen in quantum phase estimation. Maybe you should take a look at it again if you have any confusion, but very straightforward. You have the swaps and then you go in the opposite way. It is the opposite way of quantum Fourier transform circuit. And then what we are going to do is that we are going to define our order finding circuit, which we name as OFC, or you can name it as Shor's also. That's completely up to you. We define 10 qubits, out of which the first register needs to measure. So we take first register as the first 6 qubits. They are the first register. Okay, and then what we're going to do, we run according to the algorithm. So we apply the Hadamard gate. So you can see the quantum circuit here. Here is the quantum circuit, if you see. So we have seen this in the morning, right? So this is the quantum circuit, right? We apply the Hadamard, and then what we are going to do, we are going to apply this unitary, which is made using modular exponentiation. And modular exponentiation is nothing but application of controlled unitary operators, which you have studied in quantum phase estimation, right? So basically we are utilizing that, and as you can see, this circuit also looks very similar to Simon's algorithm. Okay, so that has also been discussed in the theory lecture in the morning, as you have already seen. And now what we are going to do, we are going to put the, and then we apply this X gate in the last qubit, and we put the unitary gate. Okay, so we have to use this function called unitary gate to utilize the U. We have formed the U, right? Where will the rotations come from? The rotations will come based on this unitary, right? So therefore you have to form that unitary gate. So this is how you form that unitary gate with 2 to the powers, as you have seen, and then you append it with all these qubits as the target. So these are the targets. Basically these are what? These are the target qubit. That means where you have these, basically what are those qubits? These below ones, these, the ket W, the W register. Okay, so this is basically the W register, the targets W register, where the control, where what is the control? Control is the X, right? It is the X register, first register, and second register will be the target, right? So in that manner we have done, and then we apply the QFT dagger for the first register, and we measure the first register, right? So very easy, very, the circuit is very simple. If you can see, the circuit looks similar to that what we have. And as you are aware that the order of rotation, you can also reverse it, that doesn't matter. This is all unitary rotation, therefore you can also start having this unitary in the first, and then, like, have it in the decreasing order. It goes in ascending order, as you can see the controls, but you can also do it in decreasing order as well. And then you apply QFT dagger and you make measurements. So just compare this circuit. Okay, so just compare this circuit with this circuit, and I have already given the implementation of UFAM, which is this circuit, right? So this is the UFAN or AM, any variable N or M you can take. This is the circuit. This is how the implementation is, right? And after QFT dagger, you have measurement. Okay, so now it is making sense, right? The how Shor's algorithm circuit is coming into the picture, and this unitary is the unitary matrix which we performed for a is equal to 3, n is equal to 14. I strongly recommend that you try the theoretical, try to prove this with the theory lecture which we have seen. And once that is done, then we simulate this result and we get a lot of counts of different values, and we try to take those counts which are maximum. And once we see all those maximum counts, like what are the values which have maximum count, so we are able to see that basically the highest probabilities where we are able to see are these numbers where it is all zeros, and then 19th number, this is in binary format basically, but 0, 19 and 41, that is what we actually get. And before even, like, once you take the example a is equal to 3, n is equal to 14, you can just try to calculate it classically, that what will be the period after what value it starts repeating basically. Okay, so once we do that with the help of continued and equivalent fractions, we can see it's a 2 to the power 64 is because 2 to the power 6 we are taking, because in the first register we are taking 6 qubits, right? So therefore 2 to the power, therefore that value, that zero value, that is the value which we find the highest probability with, zero value divided by 2 to the n, where n is the number of qubits in the first register. Okay, so therefore 2 to the 6, and which approximately gets into this value. Okay, and if you observe in the denominator we have the 6 number coming, and therefore the period r is equal to 6 for the value a is equal to 3 and n is equal to 14. Okay, and this can be verified, right? Because a to the power x mod 14 can be verified, right? So if you plot this value for ranging from 1 to 50, you will see that we have 3, 9, 13, 11, 5, 1. Okay, if you observe this 1, 2, 3, 4, 5, 6. So after 6, it repeats again. Can you see? 3, 9, 13, 11, like this. As you can see, it again repeats, right? So therefore, this proves indeed that for the correct period, which Shor's algorithm has given us approximately, for that period, this R value is indeed correct. Okay, so we also prove that classically also, if you observe the first 6 numbers, you can see that after that it repeats, which is the period for a is equal to 3 and n is equal to 14. Now I strongly encourage you, since this was the part of the Qiskit, and as you can see, it is not very difficult to see what is there and what is happening. It is not very difficult to see. Therefore, according to that, now the next step will be that you definitely change the values of a is equal to 3 and n is equal to 14. Maybe you should now try doing for n is equal to 15 and a is equal to 13, which we took in the theoretical example. So in the theory, we took this example. If you saw in the circuit, we took m is equal to or n is equal to 15 and a is equal to 13. So you should now try to solve a y mod m, and then construct this unitary matrix. And once you construct this unitary matrix, try to find the period and see whether it matches with the result or not. It should approximately match with the result. And therefore, for any values of a and n, you will be able to do this operation. So as you can see, the code is not very difficult. It is definitely according to the circuit theoretically which you have learned, and even the analysis which we have done in the theory, that also matches with our result. And even classically, a to the power x mod n, we apply the formula and we indeed see that yes, period is r is equal to 6 for our theoretical. When we were analyzing the theoretical, we received the r is equal to 4. Okay, that was the period, r is equal to 4. So that is now up to an exercise to you, that you verify that indeed for that a is 13 and n is 14, r comes out, n is 15, sorry, n is 15, r comes out to be 4 indeed. Okay, so this is a short lecture. This was the part which was remaining in the morning, and I promised that I will take that in the evening, but unable to take. So that is why I am preparing this pre-recorded lecture. So I hope that there are no doubts. This is very similar to what we have learned in the theoretical lectures, and I hope that you are able to connect this with the theory what we have learned till now for the Shor's algorithm. So thank you so much, everyone. And in next week, Mohammad Amir is going to cover the Grover search algorithm, and next Saturday's class will be a bit longer. I want to inform you this beforehand. It will be a bit longer. It will go beyond 1 hour, so it might stretch to 1.5 hours or maybe even 2 hours only on Saturday. And then on Sunday, I will see if I can take quantum machine learning or variational quantum algorithms. Okay, so thank you so much, everyone. Thank you.